Okay. This lecture is going to be over section 7.7. We're going to be talking in this section about complex numbers. I am writing on a tablet that is kind of tricky, and so I apologize because my writing will be all over the place and not terribly neat when I do this, but hopefully it'll be legible. Everything that we've worked with this semester up to this point have been real numbers. Some of them were rational numbers, some of them are irrational numbers, but all of them were real. What we're going to start off today with is making a definition where we're going to let I, lowercase I, be the number so that I squared is equal to -1. Now we know this can't be a real number because if I take any real number times itself, I'm going to get a positive value out of that. Okay. Whether it's a fraction or a decimal, positive or negative, if I square a real number, I'm going to get something positive. So I is not a real number. Okay. I is what's called a complex number, okay, or an imaginary number. We sometimes call I the imaginary unit. Now, because I squared is equal to -1, that means I can be thought of as the square root of -1. And so when we're doing arithmetic, we haven't run into this yet, but when we get into chapter 8, we're going to find problems where we end up with a square root of a negative number for our solutions to our equations or for other situations. And so we need to know how to deal with them when we're writing them on our page. Because I can be thought of as the square root of -1, that means when I'm simplifying the square root of -n, I can rewrite that as I times the square root of +n. So if I'm asked to simplify the square root of -5, I can write that as I times square root of +5. And now if I could do more with the square root of 5, I would want to do that. But I'm done, since 5 is a prime number. If I'm asked to simplify the square root of -12, then I can rewrite that as I times the square root of +12. And then I know that the square root of 12, if we break it down into its pieces, as we have several times before, that we see a 2 gets to come out from under the radical along with the I that we already pulled out. So the square root of +12 is 2 times the square root of 3. The square root of -12 is 2 times the square root of 3 times I. And we usually like to put that I out in front. If we wanted to simplify the square root of -20, then we say, well, that's I times the square root of +20. And if we get the 20 broken down, we find out a 2 gets to come out and a 5 is stuck underneath. Okay. And of course, some of you will get that broken down and rewritten all in one step without writing this middle piece in. Okay. But please write the middle piece if you need to do that. Okay. Understand that all of this does for us is it opens the door for us to simplify one extra case on top of what we did in section 7.3. Okay. If you're asked to find the cube root of -8, the cube root of -8 is still -2, just like it was last class and the last time I asked. Okay. If I want to find the fourth root of -16, I still stop and say this is not a real number. Okay. When we are talking about I, if I can get to the top, when we're talking about the I is very specifically defined to be the square root of -1, not any other root. There should be no i's in your answer if you are working with cube roots, if you're working with fourth roots, if you're working with fifth or sixth or eighth roots. The only time you put an I in your answer is if it's a square root and a negative number underneath. Okay. So next we're going to talk about complex numbers. Complex numbers are numbers of the form a plus bi, where a and b are any real number. By any real number, that means they can be positive, that means they can be negative, that means they can be fractions or decimals or roots or radicals. Complex numbers can look like things like 3 plus 5i, 4 minus 9i. They can be things like 1/2 plus 0.683 repeating I. They can also be real numbers like 12. Okay, 12 is considered complex because if I wanted to, I could think of 12 as being 12 plus 0i. Okay, so the real part of that number would be 12, and the imaginary part would be 0. Okay. Or I could have a number just like 6i, where again, the real part is 0, and I could think of that as 0 plus 6i if I had to put it in that form. What we're going to do with these complex numbers today is arithmetic. So we're going to do things like adding, or subtracting, or multiplying, or dividing. Okay. When you're adding two complex numbers together, okay, if I gave you no instruction at all, and I just said, hey, go try to do this, then it would be the way you'd hope it would be. And just like last class and the period before, where we said, well, we know with addition and subtraction, we can only combine terms when they're like terms. Meaning I can put the real part and the real part together and say 3 plus 4 is equal to 7. And then I can look and say, well, 5i minus 9i, those are like terms. And 5 minus 9 is negative 4i. If we're subtracting complex numbers, then we have the same issues to worry about here as we did with polynomials or any other time we do arithmetic. I have to be sure that I'm aware that that negative sign is attached to every piece inside. So I have to make sure that I change both signs and get it distributed before I combine like terms. And then I combine like terms like up above. So I have a minus 4 out of that and a plus 9i, which then when I put them together, 3 minus 4 is negative 1, 5i plus 9i is 14i. Okay. So the sum is here, the difference is here. And just like if it were an x or a y, the minus sign in front of the grouping symbols, I have to distribute to the whole thing before I combine like terms. If I'm needing to multiply two complex numbers, I'm about to figure out this pen. Okay, then we treat it as we would two binomials, or like what we did in class the other day when we were multiplying radical expressions, but we're going to FOIL. So our first terms, 3 times 4, give us 12. And our outside terms, negative 27i. Our inside terms, plus 20i. And our last terms, minus 45i squared. Now, as usual, when we FOIL, or as oftentimes happens, our outer and inner terms are the same. They're like terms, and so I can combine them together and put them into a single term. But what happens with complex numbers as well is, remember when we started this definition at the beginning and said, let's let, oops, pointed at the wrong thing. Let's let I squared be the number so that I squared is negative 1. That means when we come over right here and we have an I squared in the problem, I'm going to replace it with a negative 1. And then I can combine some more things. So negative 45i squared is negative 45, and I squared is negative 1. What that turns into then is a negative 45 times a negative 1 is a positive 45. So I can now combine my first terms and last terms together and get a 57 out of that. minus 7i. After we FOIL, okay, our outside and inside terms are usually the same, just like they were when we had x's and y's. But now our first terms and last terms are also alike after we replace the I squared with -1. Negative 45 times negative 1 became positive 45. And then we could combine them together. Oh, sorry. Last, when we do division with complex numbers. When we do division with complex numbers, it is less division in the sense of long division and more like what we did on that second problem of your Bell work, where we were rationalizing the denominator. Meaning I needed to give this fraction a different appearance, but I need it to still be worth the same amount. Okay, so whoever made the rule that you can't have a radical on the bottom of a fraction also apparently doesn't like i's down there either. Okay, no imaginary numbers on the bottom of a fraction. So we're going to multiply by a fancy form of 1 here, so that when we expand all of this and put things together, we're going to find out that there's no more i's. If you think back to that one that we did with the square roots in it, where we had like a square root of 2 and a square root of 5, okay, we picked a special expression to do that, and we had a funny name for it. Okay, we called it the conjugate. This is the other place that we're going to use the conjugate. When we're dealing with complex numbers, it's cleverly called the complex conjugate. And the complex conjugate means I'm going to keep the 4 and the 9i. Boy, I cannot write a 9 with this pen. That was better. Okay, and I'm going to change the sign in between. So instead of a minus sign, I'm going to make it a plus sign. If it was already a plus, I would have used a minus. Okay, don't forget that whatever you multiply on the bottom has to be the exact same thing on top, because I have to multiply it by I. Okay, I'm going to pause the video for a minute and write out the rest of the steps. And so I want you to do the same. Pause it here and FOIL the top and FOIL the bottom. See what happens. And if you don't pause it right here, the answer is just going to pop up here in just a second. After we FOIL, we combine our like terms in the middle, replace I squared with -1, and then combine them with our first terms. What we find out is the outside and the inside terms go away on the bottom, and all I'm left with is a positive real number. If you multiply a complex number by its conjugate, you will always get a positive number, and it will always be a real number. Okay. Now, once we get to this step, there's one more step, and it's a cosmetic step only, but it's still the required step for full credit. Okay. We don't like to leave our fractions looking, you could argue that this is messy too, but we don't like to leave it as one big fraction in one big piece. And so the requirement is that we split it apart. The -33 over 97 plus the 47i over 97. And if either of these were to reduce any farther, we would need to put them in lowest terms. If I ended up with a 4 over 8 here, I would call it 1/2. If I ended up with 6 over 4 here, I would call it 3/2. But both of these are in lowest terms, so this is where I stop with this one. Okay. The idea is that I have to use the conjugate of the bottom. I don't care what the top looks like or what it ends up being. Okay, this isn't very pretty, but -33 plus 47i is fine on the top. But I'm not allowed to have that 9i on the bottom, and so I can get rid of it by using the conjugate. This is the second place that we've seen that. Okay. I know this isn't very many examples, but go back and replay them if you need to. Look at them a little bit more closely and compare them with some things in the book. I will put some problems in Canvas that have some problems for you to look at that are similar to these from the textbook, and then you can check your work and see how you're doing with them. I'll be back next week, and then we can talk about this a little bit more if we need to.